Okay, now I'm going to do another video on binomial. Just one more before we have a little test tomorrow. If you're watching this on Thursday. So this one says, a camping ground owner has kept a record of how many people stay each night in each of his cabins. Each cabin contains 6 single bunk beds. The probability that a bunk bed is occupied is 0.35. On any given night, what is the theoretical probability that a cabin has just one bunk occupied? I'm going to zoom in because it's easier to write when it's zoomed in. So this tells me I'm trying to work out the probability that x is equal to 1. Remember, equals is b p d less than or equal to is b c d. So trying to work out the probability x is equal to 1. Go into my calculator. Distribution, binomial, and because I'm doing equal to, I'm doing BPD. My x, I'm looking for exactly 1. My number of trials, he's got 6 single bunks in each room, so it's 6 trials, and the probability that a bunk is occupied is 0.35. So I've got 0.35, press equals to get 0.244. That one was nice and easy. Okay, question B. On any given night, what's the probability that a cabin has at least 3 bunks occupied? At least 3 includes 3, so that's x is greater than or equal to 3. Now I need it to look like this for me to use it in my calculator. So if I look up here, that means I need 3, 4, 5, 6. Now that means I'm going to work out the probability of this part and take it off 1, because in total this is going to equal 1. So I'm going to write it's equal to 1 minus the probability that x is less than or equal to 2. So go 1 minus, I'm going to work out in my calculator. So I need to go distributions, binomial, and now I'm using BCD because I have it looking the way I need it to for my graphics calculator. It needs to be less than or equal to, So BCD, x is now 2, number of trials is still 6, probability is still 0.35, and I get 0.647. So I need to work out 1 minus 0.647, which is 0.353. Okay, this one says calculate the theoretical probability that a cabin is unoccupied for 2 consecutive nights. So unoccupied means that the probability that 0 bunks are occupied. So my x is equal to 0. So because it's equal to, I need to go into PD. I'm looking for 0. Still 6 bunks, still probably 0.35. 0.0754. Now, this is saying for 2 consecutive weeks. So we multiply the probabilities together. First week is 0.0754. The second week is also 0.0754. To find the probability of 2 independent events happening together or in a row, I multiply the probabilities. So 0.0754 times 0.0754. That's the same as doing it squared. So that's what I'm going to do when I go to my calculator. So 0.0754 squared. And now this is a problem I've had a few emails about. This is the correct answer. it just looks a bit funny. We need to change it from standard form to regular form. This -3 here means the decimal point has been shifted 3 places. 1, 2, 3. So it's going to become 0.005. What was the next number? 57. I'm just going to do it to 2 figures. See how if I move that 3 times, it's going to be in between the 5 and the 7. -3, it's been shifted 3 times. You can always think it's -3, 1 less than whatever the negative number is how many zeros there's going to be between the point and the number, or just how many zeros it's going to be. There's 1, 2, 3 zeros, and the point goes after the first one. Okay, question D. The graph shows the observed. So these boxes represent the experimental probability, what he observed in his cabin. So he actually observed 0.246, 0.07 on of the time there was 0 bunks occupied. So it's asking us to complete the graph. So the lines are the theoretical binomial distribution. So he's done 1 and 2. So we're going to do 0. We've worked out 0.50754. We worked it out here, but x equals 0.0754. So very hard on here, but I'm going to, it's just a little bit above the line, just a tiny bit. Okay, next 3, I'm going to go into my calculator. So menu, stat, distribution, binomial, BPD because it's exact values, and I'm going to use 3 instead. And 3 gives me 0.2354. So 0.2, it's really hard on the screen because I can't see the lines. Let's just say it's here. It's easier in your book to see where the lines are. Okay, 4, same thing, very easy. Go back, change it to a 4. 0.095. So here's 1. So it's here. Oh, a wonky line. Use a ruler in your book. It's a very wonky line. And 5. 0.02. So it's just underneath the line. Very wonky. I wish I could do a better job. Okay, and then the last one is going to be almost insignificant, but it's going to be much less. So it's like way down here. Okay. This one should be up a bit. Close to the line. It's very close. It should be close. These two are close. Okay, and finally we're going to compare the two. So remember the boxes that are originally drawn are what he observed in his cabin, and these lines are the theoretical probability of it happening. So this is what he expects to see. These lines are the amount, the chance, the probability he expects to see this many people. So what we have is we have both distributions, the experimental and theoretical, have a mode of 2. It's the most common. They're both positively skewed. So it does, the experimental one does kind of fit the look you'd expect a binomial distribution to be. You'd expect it to be have a single mode, and potentially it could be positively skewed. That's something that can happen. So the model fits well for 0, 1 and 5. That's why I made such a point of saying it should be close, because my squiggly line made it not look close, but it does fit well for those 3. And then for 2, 4 and 6, so the probability was meant to be just over 0.3, but he saw closer to 0.4 of the time there was 2. And the model was meant to be just below 0.1, but it was actually over. He saw more than he expected groups of 4, and he saw way more than he expected of groups of 6, according to the theoretical probability. So for 2, 4, and 6, they were more likely to stay. There was more likely to have 2, 4, or 6 people than expected. This might be because people travel in pairs, and for 3, it's less likely to happen than expected. So because it's not that good for most of the values, or for over half the values, maybe the binomial distribution isn't so good to model this situation. And that's page 54.